So far, we've been learning about rules that help us understand the uncertainties of numbers we're using in calculations and uncertainties of numbers that we're actually calculating. And we've had to make lots of assumptions about what digits are significant or non-significant and how much error is associated with the numbers we're using in calculations. And as you might imagine, this isn't the most accurate way to go about things. There's a much better way to understand the uncertainties of numbers, and I'm sure you've seen it before. When researchers know the exact level of uncertainty in measurements they've made or calculations they've produced, they often report that uncertainty along with the values that those uncertainties describe. For example, the researchers that estimated fuel needs for the Mars orbiter might know exactly how accurate that number is. And instead of just writing down the number 200, they might write down the number 200, followed by a plus minus sign, followed by another number, in this case a 5, which indicates the exact amount of uncertainty associated with that value. This is telling us that the true amount of fuel will lie somewhere between 195 and 205 tons. When we report a value along with an error, as we've done in this example, we can add and subtract that error to find a range of values. And the true value of that calculation or measurement will fall somewhere in that range. The weight of the empty spaceship might also be expressed this way, although most likely we're going to know the weight of the ship with a little more certainty. So in this case, we can write down the weight of the ship is 1.5 plus or minus 0.1 tons. And we're assuming that this value and the error are coming from experts who either built or measured the ship. When we have what we refer to as absolute errors, which are what's presented in this example, we know the exact error associated with the numbers that are used in calculations, and we can use these errors to find the exact errors and uncertainties associated with our results. Once again, we've written down a couple rules for you guys, and in this case, they're describing how to calculate the errors of final results when you're working with explicit errors like these. When adding or subtracting values, you're going to add the absolute errors in order to find the error associated with your final result. This is just as easy as it sounds, and we'll go through an example in a moment. When multiplying or dividing two numbers, we're actually going to add what we call the fractional errors of those two numbers to get the fractional error of our final result. And we'll define what we mean by fractional error when we go through an example. And before we actually do calculations, we want to introduce an important side note here. What we're going to do is we're going to save all of our rounding for the end. And so what that means is we're going to keep all of our digits, or as many digits as we're willing to write down during our calculation. And at the end, we're going to round our final error to one significant figure. And then we're going to round our result to the same level of precision as that error. All right. Now let's work through some calculations that mirror what we did in the last video. First, let's add the weight of the fuel to the weight of the empty ship to try to find the weight of the fueled ship at takeoff. We have 200 plus or minus 5 plus 1.5 plus or minus 0.1. And we can start by first adding our two weights together. So we have 201.5. And then we're going to have plus or minus some error that we still need to determine. If we follow our rules for addition and subtraction, we know that we need to add our absolute errors to find the error of our resulting calculation. And absolute errors are just these errors that are already listed. So we're going to go ahead and add 5 and 0.1 to find an error for our result, which is equal to 5.1. Lastly, we need to follow our note here on the left and round our final result and error. We round our error to one significant figure, so our error becomes 5. We're also going to round our final result to the same level of precision as our error. And because our error is precise to the single digits place, we're going to go ahead and round 201.5 up to 202. We can see that the true weight of a fully fueled Mars orbiter is somewhere between 197 and 207 tons. All right, now let's look at multiplication and division by dividing our empty ship weight by the result that we just found. In this case, we'll divide 1.5 plus or minus 0.1 by 202 plus or minus 5. This will tell us the fraction of the total weight that is represented by the ship alone. Like we did before, we'll begin by calculating a value first, and we'll worry about the error a little bit later. So we'll divide 1.5 by 202. If we plug that into our calculator, what I get is 0.00743, and plus or minus some error that we still need to determine. Okay, and when we're doing multiplication and division, we find our errors a little bit differently than we do when we're doing addition and subtraction. Instead of adding the absolute errors, we add our fractional errors. Now, fractional errors are a little bit different than absolute errors because they express error as a fraction of the number that they're describing. So to find the fractional error of the empty ship, what we do is we take the absolute error, which is 0.1, and we divide that by the ship's weight, which is 1.5. Similarly, we can find the fractional error of the fully fueled spacecraft by taking the absolute error, which is equal to 5, and dividing that by the weight of the fully fueled ship, which is 202. If we add our two fractional errors together, we will get the fractional error of our final result. So 0.1 divided by 1.5 plus 5 divided by 202, punch all this into a calculator, and what I get is 0.0914. This gives us our fractional error, but we almost always present errors as absolute errors when we're writing out numbers. So to find our absolute error, we're going to set up a simple relationship. Okay, our fractional error, which we found to be 0.0914, is equal to our absolute error, which we still need to find, divided by the result, which we calculated earlier, so 0.00743. I can do a little bit of algebra and rearrange this relationship to show that the absolute error is equal to 0.0914 times 0.00743. Once again, I can punch these numbers into my calculator, and I can find that our absolute error for the result is 0.000679. Just like earlier, I'm going to make sure that I round my final error to one significant figure. So my value becomes 0.0007 because we're rounding up. And just like before, we're going to round our result to the same level of precision as our error. Our error is precise to the fourth decimal place, so we round our result to the fourth decimal place, which leaves us with 0.0074 plus or minus 0.0007. If we want, we can get fancy and express both our result and our error as percentages, in which case we'd multiply both those values by 100. So we would have 0.74 plus or minus 0.07%. And once again, we found that our empty space shuttle is a small fraction of its fully fueled weight. Now, as you saw, when you're doing multiplication or division, calculating the absolute error of your result can be quite involved. We went through several steps in the above calculation. But what I'd like to do is make this calculation a little bit easier for us in class. So what I'm going to do is I'm going to combine all those steps into one formula that you can use for calculating absolute errors when you're doing multiplication and division problems. Using this formula, the error associated with our final result is going to be equal to the value of our final result times, in parentheses, the error of the first value that went into our calculation divided by the magnitude of that value, plus the error of the second value that was used in our calculation divided by that second value. Inside the parentheses, we're calculating and adding our two fractional errors, and then when we multiply by the result, we're converting a final fractional error back to an absolute error that we report with our final value. If we wanted to use this formula for the calculation that we carried out above, our result would be 0.00743. Inside the parentheses, our first error would be 0.1. We would divide that by the value that that error describes, plus for our second value that went into the calculation, we would have 5 divided by 202. If we punched all of this into a calculator, we would end up with the error that we calculated earlier, which was 0.007, after, of course, we've rounded to one significant figure. All right, we will do calculations similar to these in class. I threw a lot of material at you guys in these videos. So if anything's unclear, please, please, please come to class with questions. That is what our class time is for. All right, I will see you then.